Thank you everyone for joining our webinar today, wherever you might be on the globe. My name is Tom Burchard, and I will be the moderator for today's Elmarco Talks webinar, featuring my colleague Josh Manasco, who will be discussing the latest innovations for industrial electrospinning. So as this is actually the last presentation of this season of the Elmarco Talks webinar, we are looking for topics for season 4. If you have any suggestions, we would love to hear them. Please feel free to contact us at the marketing@elmarco.com email you see there, or any of our social media on YouTube, LinkedIn, Twitter, Facebook, all the usual places. We'd love to get your ideas of what you'd like to hear about, and we'd be happy to present that at a future webinar. So I want to just quickly introduce Elmarco again while everyone's kind of joining in here. We'll just go through a couple of highlights here on Elmarco. We just recently celebrated our 25th anniversary of Elmarco being in the market. That's not only with electrospinning, but with some of our other businesses that we were connected with early on. In terms of the electrospinning, we have over 30 patents registered globally. We have over 280 machines installed. That includes approximately 15 industrial lines, and we have 85 employees between our 2 facilities here in Liberec. I think, as everyone knows, Elmarco is a very global company. We have offices in the US, Italy, the Czech Republic is where our headquarters are, and we have partners in both in Japan and in China. Most of our customers, especially the industrial ones, tend to be very secretive about owning Elmarco equipment, so the list of references there is relatively short. However, on the lab side of things, many more universities and those types of institutions are happy to share that they're using Elmarco equipment. So feel free to reach out to any of these companies if you'd like some potential references on the operation of our equipment. So I think everyone is pretty familiar with the Elmarco equipment. I shouldn't need to go into a lot of detail here. And in fact, Josh will talk a little bit more about the Elmarco trademark nanospider technology that involves the free surface electrospinning process. Again, I'll let him cover those details when he gets to it. Basically, our product line consists of a 30-centimeter single wire lab tool all the way up to our flagship industrial machine, which is an 8-wire 1.6 meter wide machine that again is primarily for industrial applications that you see there on the bottom picture. And one of the best things is that same technology that we showed in the previous slide is used on all these machines. So scaling up from one to the other is a very, very straightforward process, and really there's been almost no incidents of problems where we've not been able to scale something up. So again, we feel very successful with that scale up process on our equipment. I think everyone knows that there are many, many applications for nanofibers, including air filtration, liquid filtration, performance apparel. I think another emerging area is really in the medical applications, specifically wound care. We're always looking at things in energy in terms of battery separators, and also finally acoustic materials. That's something near and dear to my heart, as that's one of my former careers in the acoustics business. So with that, I just want to add one quick note that if you have any questions during the presentation, please feel free to drop those into the chat box, and we'll get to those questions at the end of the presentation. So without further delay, I would like to hand over the presentation to my colleague, Josh Manasco, who again will be talking about the latest innovations for industrial electrospinning. With that, Josh, I'll let you go.
All right. I hope that everybody can see my screen. Yeah, thanks, Tom, for the introduction. Again, please ask as many questions as you can. Otherwise, I've got Tom loaded up with very softball questions to ask me, and we'd rather have something more tough, let's say. Just want to talk a little bit today about some innovations that we have. It's related to the market. We'll talk a little bit. I hate to start with a marketing slide, but when we talk about the market, we really want to look at not the overall numbers. Those can be kind of fluff in some of these these market reviews, but it's to see that that the market is changing a bit. You can see that the orange part is filter media. That's always been a big core part of our business. When I joined Elmarco in 2014, I would say that 90% of our business or so was in air filtration, maybe 80 to 90%. And you can see how the market's changing. It's growing, and there's the face mask stuff there. That's probably not as accurate, but the medical textiles, those types of things are growing. So we have to look at this because we need to know what these applications need from an equipment innovation standpoint. And we like to understand, of course, it's great to have good growth, but we need to know where the markets are growing specifically. It's not always going to just be air filtration. And that's still a big business for us, but it's something that our equipment has been doing for a long time. And just to show a little bit more about the market from our standpoint, this is probably could be updated a little bit, but since 2018, we've sold a little bit more than 34 installations. But this is more to talk about not so much about what we've sold, but about the diversity of the applications that we're seeing. Microelectronics is becoming a big thing. Of course, Tom mentioned medical, consumer products. I mean, we're seeing nanofibers even in diapers now. We get cosmetic face masks. Performance apparel is a big thing coming from the PFAS regulations. And of course, we still have our core business in air filtration. So this is just a reference slide to show what we're seeing, that not only is the market report saying that there's a change in or a growth in other areas, but we're starting to see it in real business on the industrial scale. So I'll talk a little bit about the nanospider technology, and then we have two technologies now in our portfolio. One called Linea, which is our standard, which if you have our equipment, most likely that's what you have. And there's Infinity technology, which is something we'll discuss about. Some process innovations that help us, that we see helping us to meet some of the market needs for these different applications that are coming. And then I'll talk a little bit about our turnkey industrial line, just as a finish, a wrap up for what we provide as a service to our customers. So about the nanospider technologies, Tom started to briefly touch on it. If you're familiar with our technology, this will just be a review. But in our standard equipment, and I have a video to illustrate this a little bit later, but we have a coating head. It's a coating technology. Normally, we're coating onto some substrate that could be a nonwoven, a paper, a film, something like that. That we're passing that film in between two electrodes, the spinning electrode and the collecting electrode, and that substrate gets in the way, let's so-called in the way between those two electrodes, and the fibers are attracted to the collecting electrode from the spinning electrode, and they collect onto the substrate and form anywhere from fractions of a gram per square meter for air filtration, some air filtration applications, up to 10, 15 grams per square meter membranes for, let's say, breathable hydrophobic membranes or separators or anything like that that would actually require more of a membrane. So there's other technologies in the market that can be used to make nanofibers. We think that, or from what we've seen, a lot of them aren't scalable because they're open systems. Our first technology was an open system, but we manage it quite well. But a lot of these other ones are quite difficult to manage in an open system where the solution would be changing constantly. And it would be difficult to produce really at the industrial scale. Great for lab trials, but not really a good way to scale up for making commercially viable products. And then also some of these, like centrifugal electroblowing, they have already been commercialized in some applications, but you're not really able to achieve that really small fine fiber where we're talking about 100 nanometers and below, which is what we're considering that electrospinning is most useful for in most cases. So the main two are needle and needle free. So we have our free surface electrospinning. We see the advantages as the throughput, the jets they optimize based on physics. They are self-optimizing in the process. We don't have to clean any types of orifices or needle tips. There's no clogging. And we really think that our solution is better for the industrial scale where you're going to be producing 24/7 and having to maintain this equipment and make sure that the equipment's working properly, throughout the whole process of the day. And this is just another review. If anybody's ever knows anything about electrospinning, you can see these videos everywhere. Every university in the world has a setup similar to this. You can see that you're defining where the jet's coming from. It's coming from that tip of the needle. It's taking a long path from the tip of the needle to the collector. Either the collector is oppositely charged or grounded in this case. And you can see that the fibers are taking this what's so-called a whipping instability and taking a really long path between the needle tip and the collector where it stretches from, sub millimeter to sub micron fibers. So just to talk a little bit about the linear technology and the infinity technology, we showed this image before where the coating head is moving back and forth and coating a wire. And when it coats the wire, then we have an electric field. You form the jets along the wire, you spin and you coat. In this case, that we're coating continuously by moving a coating head through the process. Well, and that's the linear technology. That's what our technology has been for the last 10 years or so, or even maybe 15 now, I would say. But if you look at infinity technology, that's where we're actually now moving the wire very, very rapidly through the process. So we're coating it on one side. It's like a loop. We coat it on one side, we clean it on the other side, but both loops, both sides of the loop, when it's passing through the, let's say the spinning zone, is coated with solution, and that solution spinning. So it's the same process, same physics, same technology. However, in this case, we're not moving a coating head and interrupting the jets constantly. We let the jets form when they're coated, and then as they pass through the process, you don't really get that constant interruption of the spinning back and forth. And so we see an advantage in that, and I'll talk a little bit about that in just a moment. So this is just a video of our linear technology. You can see that the wire is being coated by a carriage going back and forth, and every time that carriage passes through, it stops the spinning and restarts afterwards. And so you can see that the jets look like they're coming in three dimensions. The substrate in this case is above the wire, and it's everything, even if it looks like it's going down or into the screen or away from the screen, all those fibers are still being attracted to the top. And that's another advantage is you have these self-optimizing jets that form, wherever they need to fit based on physics and the way the process is designed. And that allows you to have the best uniformity in our opinion and what we've seen our customers have told us in comparison with other technologies. And I think this video might be a little slow, so if you want to go to our website, we in the practice session it was a little bit slow, but really it just want to illustrate that you can see the wire moving through. There's no coating head moving back and forth. The wires moving through the process and continuously being coated and continuously being spun into nanofiber without interrupting those jets. And so we see that as a particular advantage when it comes to producing defects where you don't have a constant stop and start. It also allows for more stability of the process because of that. And also with that reinitiation of the jets, every time you stop them, we have seen that it can cause defects to form whenever you're stopping and starting those spinning jets. So what we really see with this process is that we see it, one of the main ways to control throughput is voltage. So the higher the voltage, the higher the throughput, but then also the more defects because you're causing a more chaotic process. And what we see is that's this extra stability of not stopping and starting those spinning jets all the time gives us the ability to turn that voltage up a little higher or to maintain the voltage but see less defects being produced. But also we see a little bit more throughput because we're not interrupting, again, stopping and starting the process all the time. We also see that we've through this extra stability, we've been able to have a bigger spinning window. What we call a spinning window is the ability to spin at higher or lower concentrations or higher or lower relative humidity. And those directly impact fiber formation. They impact fiber diameter mainly. And if you have a bigger window, it allows you to push the fiber diameter further down or further up in the process, and then also be able to spin, sometimes even spin materials that aren't able to be spun on our linear technology, which was a benefit we weren't expecting necessarily. It wasn't the goal. Our goal was to reduce the defects. But in this case, we've also seen that we get benefits in throughput and bigger flexibility in our ability to form fibers at different sizes with different materials. It also is another added benefit that we found that some materials that don't spin at all on the Linea machine now are able to be spun and produce higher quality materials on the Infinity line, which is another added bonus. And this is just one example on the light table looking at two materials that were produced from the same solution, 16% PA6, 6, and we were PA6, sorry, PA6 at at a low relative humidity, which tends to cause a lot of defects in our linear technology. So we wanted to test an kind of extreme condition to where we know we generate a lot of defects, and you can see that there's quite a few less defects that are produced running the same conditions with the same, let's say, very difficult settings on the line. And these are some of the examples of the microscopic defects that can form. And the reason these are important, if you're talking about a hydrophobic membrane where you're trying to block the water from penetrating the membrane, or even if you're talking about a high quality air filtration material like a HEPA material, or liquid filtration where you're trying to, have a certain log reduction of bacteria, for instance, these holes that can be generated from these defects, either because they have a different mechanical um, properties than the rest of the web, or because they form some hole even whenever they're just formed whenever there's like shrinkage from evaporation of the solvent, for instance, that can cause holes. You can see that if the mechanical performance is different between areas where there's defects and the fibers, then whenever the materials, let's say, handled downstream in pleating or making of filter packs or even lamination, then those can end up in ruptures in the membrane, and of course, then that's a failure point for those types of applications. So it's something that we've been working on. That's the intent of us to design and build this type of machine for working on these types of applications that are very sensitive to any type of holes or any type of ruptures in the membrane. So again, benefits, we increase the throughput of non-interrupting jets. Just to sum it up, reducing the number of defects for these critical applications. It helps with the stability of the spinning jets, which also helps us with making some polymers actually electrospinnable, we would say. And then we also see an expansion of the electrospinning window, as I described, where you can use some different solvents, polymers, and concentrations to see if you can make larger or smaller fiber diameter than you probably can reach otherwise with a standard linear technology. So just to talk about some process innovations that are related to just the overall technology. So if we're going to be talking about defects, then we need to find a way to quantify the defects. Qualitatively, we see, okay, it doesn't produce as many, but how many does it produce and what type of defects are being produced? So we have something called a Uniscan device that we have on our industrial line in our headquarters in Lieberitz. And basically, it's just a visual inspection machine where we have three cameras that are, we can get a resolution of about 50 microns, or around 100 microns is safe to see the size of a defect and to capture it and to quantify it and characterize it. So when we're looking, it's a reflection mode. It's mounts at the end of our equipment. It's quite easy to use. It took quite a bit of development to be able to build libraries of these defects and everything. But it's quite handy for us to verify that we're seeing what we're seeing in the process. So it can be a quality aid, it can be a process aid for whenever if there's something wrong with the process or something with the quality of the material. So these are the types of things that we've found, some fibers, some extra fly of fibers, some holes, dark spots, things where there might be wrinkles in the process. So that's where you can use it to find out are you forming some wrinkles somewhere in the substrate that's causing you to have these sort of non-uniformities? Is there something wrong with the process that's forming more of the film-like or droplets? Are you getting some pressure points somewhere that are causing the fibers to be disturbed? Those kinds of things, which are quite interesting to look at when you're talking about these high-end membrane materials. So it's just an example of a role that we mapped where you can see, you can capture, this was off of the linear line. You can see that there's a wrinkle there. There's a couple of spots here and there. You see on the edges, you can tend to get a little bit more defects where the process is stopping and starting. But it's just an example of what you can capture and see with this type of inspection system. So this is where we can use it as this is kind of a case study where we were looking to see what was wrong with the process we were having. This was a typical sampling that we do. So we do sampling for our customers and run trials for them to produce materials, of course, for their testing. So we kept seeing this cyclical large amount of defects that kept forming in the roll. And we were saying, okay, this is you can see it's got a certain period to it. So there's got to be something going on in the process. It wasn't normal to see this type of cyclical defects collection. And you can see that in this case, though there's in our equipment, there's the part where the wire comes over a pulley, and that pulley has a certain diameter. And so we started to think, okay, is there something going on with that pulley that's moving the wire, affecting the wire during the process whenever the wire, because we have a continuous feed of and even in the linear process, we have a continuous moving of the wire to make sure that we don't collect any, let's say, junk or trash or anything like that, or dried polymer when we're coating the wire. So as that's moving through, we could see that there was a pulley that might be that there could be some correlation. So we stopped moving the wire just for this period of time where we were making these trials. And you can see as soon as we stopped the wire moving, that this periodic cyclical type defect collection completely stopped. So in this case, we were able to diagnose what the issue was in the process based on feedback from this visual inspection system. So it could be quite powerful if you're having some issues with your equipment or some run that you're making or trials you're running to see, okay, what's going on here? This isn't normal. So another innovation. This is related to Linea. We call it the Linea membrane line. When we first started designing our equipment and running our equipment, we really designed it for producing nylon for air filtration materials, and that was sort of the basis for design. So we had to have some way to work on the spacing of the wires in the machine. We have 8 wires in our Linea machine in the machine direction. So we have to figure out what's the best spacing. So we kind of did that and figured it out for air filtration and nylon. What is the best spacing to do? And that's the optimization we did with our equipment. But we've been thinking about how can we potentially, it's kind of like a no-brainer for somebody who doesn't know about the process necessarily to say, let's just put more wires in that machine. Why not? Because you're getting, it's so certain amount of nanofiber spinning from each wire electrode. So we thought, okay, well, to ourselves, nylon, it doesn't help to put more wires in there because we've done all that testing in the past. But we decided now that we were working with a lot more materials, different materials, that we would check and say, hey, are we sure that the spacing is optimal for any type of material that we might be spinning? When you're spinning, you can look from the side of the machine through the window. You can look through each side of our equipment. It's got clear windows, and you can see that there's a certain plume size or certain like shower looking size of the jets whenever you're spinning, and those are different for each type of polymer and solvent system. So we thought to ourselves, let's retest our hypothesis that that the spacing is optimal for all polymers, and let's test to see if there's some spacing that might be better for a particular polymer system. So in this case, we decided at the lab scale to change the wire spacing quite a bit to see, to take it in half, to make it, the one wire is like in a big space. There's no other wires close to it. Okay, what happens if we put the wire 60 millimeters apart, 120 millimeters apart? And we see that for nylon, okay, there's a little bit of change here and there in the throughput. This is what we're looking for, is to get more fiber spinning. But in the case of this polyurethane system, it's the PU plus UM. You can see that we more than doubled the throughput by putting the wires closer together, so we could fit more wires in the same space and not impact, and still get a lot of throughput from the wires themselves, each individual wire themselves. But whereas nylon, you put them closer together, you don't really get any increase in the overall throughput for the number of wires you have. And then we didn't really, we were looking to see, do we really sacrifice the coefficient of variation for the basis weight of this material? And we see that, we can still get, for this polyurethane system, we can still get a much higher throughput, but without sacrificing really the coefficient of variation for these materials. So we wanted to implement that on our industrial line, which we've done. So we came up with a system where you can have a flexible wire spacing. This is that that on the left side you can see that's a cylinder. There's like a cylinder there with different notches on it. That's where you can place different numbers of wires. So we designed this so that we can have a testing machine on the industrial scale to prove this out. And then on the right side is just the standard machine where you have four wires. So this is a one machine would typically have eight wires total. It has four on the right, which is a standard setup, and on the left is a customizable setup where we can change the spacing to try different spacings at the industrial scale. And so the case study we had is that we were looking at this polyurethane replacing PFAS materials for, let's say, some microelectronics, potentially some performance apparel materials where you need a breathable, waterproof material. We were able to push the limit a little bit and get 1.5 to 2 times lower or higher throughput, so that's a 1.5 to 2 times almost drop in the cost to production, with our goal to be less than $3 per linear meter, which is relevant to the performance apparel market. So we were able to maintain, these are different examples of data on the right side where we were able to, target was 10 meters. We were able to make materials that are around 10 meters that are still washable, that don't lose all of their hydrophobicity after laundering and drying. So we just proved to ourselves that we could do it at the industrial scale for this type of recipe, where we found that it does have an advantage to squeeze more wires into the machine to get more throughput in general for this type of system. And then this is another one, it's kind of a reminder of a technology we have that we haven't talked about in a while, and we continue to refine this. Let's show a video. Sorry if that's loud. But this is not what you want to see when you look in your equipment. These are fibers that are not going to the substrate. They're not being collected. So that's just sort of making a tornado in there. That means that the substrate you're collecting on is acting like a resistor, and it's blocking the collecting electrode and the spinning electrode from seeing each other, let's say. They're not able to really form a good electric field between those. And that's gonna make it a problem, because then your fibers are gonna look for other places to collect in the chamber and make a big mess. So we were thinking, how can we, just a little bit more about the impact of substrate. So in the top case, you have a conductive substrate where you can make a good electric field between the collecting electrode and the spinning electrode, and you can see that it sort of forms this sort of plume where the fibers come out. They expand a bit, but then they're trying to come back and collect on the wire electrode above. So that's the sort of the shape of the field whenever you're spinning. You can see it in the machine, and that's a good case. That's the case where you're probably spinning well. You're making a good coating, and the substrate's not blocking the communication, let's say, between the two. But in the case where you have a material that, like I was mentioning before, that's highly resistive, it's completely blocking the two, and you're forming a barrier between the two electrodes. And you're not going to get good spinning, or you might get some very light coating, but it's not going to be uniform, and it's going to be quite a mess, most likely, in your equipment. We came up with this design for a conductive belt electrode. We call it endless belt because it's a loop. But in this case, this is where you have the substrate actually in contact with the collecting electrode. And that allows and it's a conductive belt, so that allows you to discharge the substrate continuously while you're spinning. So you would still charge that belt of the opposite charge of what your spinning electrode's charged at. But in this case, it enables us to be able to spin on thicker materials that weren't possible with the standard wire collecting electrode. And it allows us to have some flexibility with different types of substrates that might be useful in other applications. We don't have any issues normally with any spun bonds or melt blowns, for instance, but there can be some films or some other things that you can try to spin onto that are resistive, or very thick nonwovens that can be a difficulty to coat. So just to remind everybody that this is a technology that, and that helps us to expand our application space, because it allows us to spin on things that we weren't able to in the past, that might be part of a composite or a material that would go into one of these applications. And you can see also that there's sort of electrospinning kind of copies a bit the whatever it's coating. So the more uniform usually the substrate is you're coating, the more uniform the nanofiber layer is going to be. And in the case of the belt, you can see it has a very plain pattern. You don't really see a pattern there on the material because it the belt's very uniform and it collects very well onto the material, and you don't see any sort of impact of the substrate. In the top case where we're spinning with a wire collecting electrode, you can also sometimes see a pattern from where the substrate has some wrinkles or some non-uniformities, and that can also be an advantage for using the collecting electrode, the belt collecting electrode in this case. And then also even at I should say micro scale uniformity, but looking at the micro scale uniformity, you can also see sometimes where there's some hole in the substrate or some bigger gap between fibers of a spun bond, for instance, where you can see that the fibers will sometimes coat lightly in some spots and heavily in others. Sometimes when you're using this belt, you have a nice uniform material behind it, so it's really gives you a nice uniform coating, and so you can see that you can even get higher uniformity in some cases with the belt than you can achieve with the wire electrode, depending on the substrates and the materials that you're spinning. And this was in the case where we had a material that we were working on for a customer. We were looking to get a high hydro head, which is waterproofness. And you can see for very similar air permeabilities, we were spinning on the endless belt versus the wire, and we can get even higher hydro heads. And we were basing this on uniformity differences at the micro scale, where we were able to make better waterproof membrane or barrier in those cases for this particular combination of fibers and substrate. So it's a case study where we proved out that in this case this gave us superior performance. So just a summary, we of the process innovations, we have now a visual inspection system that can help with the critical applications. It can be both a quality tool or a process control tool. We are working on the linear membrane line, LML, that allows us to produce sometimes with these different solvent systems that are not, let's say, our typical nylon recipe, where we see that you can get much higher throughput by putting more wires in the machine. We have this as a prototype so that we can test it. If you were interested to test something that you're working with and to see, we have both lab scale and industrial scale testing capabilities for this prototype. We have a conductive belt electrode. We have those as in both of our lab and industrial machines, where you can see that it gives you the opportunity to spin and coat materials that maybe you weren't able to do in the past using the standard wire-to-wire collecting electrode. So all of these things we see bring us to giving us more tools in our pocket to be able to work with different materials, to make materials faster, lower cost, to analyze these materials, quality and performance, and to be able to potentially do things we haven't done in the past with combinations of these different innovations. So just to wrap everything up, Elmarco, just a little spot for Elmarco. We really are looking to supply the turnkey system, whether it's the endless belt that you need or it's some sort of quality tool that you need. We want to bring all these things together. We don't make all of these things ourselves. We make a lot of the equipment that we sell. We don't make unwind rewinds. We don't make waste air treatment, those types of things, but we do build a lot of the core things like adhesion modules and the spinning material, the spinning machine, and a way to make polymer, to mix your polymers, a polymer mixing station, the dryer if you need to dry the material after it's been spun, or an AC. It's very critical to have a very fine control of the relative humidity and temperature when you're spinning. So we design and build our own air conditioning systems that are precisely control that. But we would like to, bring the total package. We have a lot of design people. We do layouts for people. We do lots of things. So that's our core business, is to deliver these turnkey systems with any innovation or custom. All the lines are customized almost every time. So we want to deliver that to our customers. And just to kind of show the modularity of our system, we think of like Lego blocks for our lines. We can put extra, to increase the throughput or make more nanofibers, then you just need to put more spinning units in line. So if you had 1, 2, 3, or 4, then that gives you 8, 16, 24, or 32 electrodes, and that's just how you can increase the throughput or production speed for your application. So with that, I'd like to say thank you, and I hope that this was useful for everybody, and I'd like to take any questions that could possibly be on the table. Thank you.
Great, Josh. Thank you so much. That was really super informative. Even I learned a few things every time. Every time we talk about all these topics, there's always something you pick up that you hadn't thought about before. So thank you for that. I think everyone else enjoyed it. So I'll just kind of run through a couple of the questions. There's even a couple of things that even I can answer with my level of knowledge. One of the questions was on tool nanospider equipment for academics, and certainly we have the NS Lab. That's the single wire, 30 centimeter wide machine that is actually designed for academic use and basic level nanofiber research. I would encourage everyone, and particularly the question answer, if they want to look or find out more details, please just go to the Elmarco website or contact us at sales@elmarco.com. We'd be happy to send over a budgetary offer for that equipment and fill you in on any more details. So Josh, the next question was about biopolymers, and I know we've done some work around that area, and I think at least from my view, our general answer is if someone has electrospun a polymer on a needle apparatus, there's a very high likelihood that we can spin that same polymer on our equipment. But I don't know, Josh, do you want to maybe comment more
Yeah.
on the biopolymers?
Yeah, I mean, we've encountered almost anything you can think of if you can dissolve it in a reasonable solvent, meaning something that's not super flammable or is going to, dissolve your skin, then, we can generally work with it. PLA, PCL, we do chitosan, cellulosic materials, different types of materials, and to make a note about the converting from the needle. Yeah, I mean, I would say 99% of the time we can do it. It's usually a just slight adjustment in the machine settings, maybe an adjustment in the conductivity or viscosity or concentration of the solution, maybe to change a solvent. The one challenge I would say that we do see really from going from a needle spinning to a free surface spinning would be more about volatility of the solvent. If you're spinning at a pure acetone or THF or something like that, where it's extremely volatile. The one thing that is difficult is that it can dry on the wire before you can spin it because it's so volatile. You're coating a very thin layer on a metal wire, and you have to. And so typically in those cases we would add a little bit heavier solvent in the mix or switch the solvent system to something that we're familiar with. So the one thing we have been really working on is to eliminate the REACH list chemicals to kind of go along with sustainability. Is to say, we want to try to use as friendly a solvents as we can. Okay, if you can't use only these benign solvents because it's a particularly difficult polymer to work with, highly engineered polymer, then we have to use what we have to use. But in general, we've developed recipes that don't have REACH listed chemicals like DMF, NMP, DMAC in them. So that's another initiative that we have that we can try to help in the market with, that we are developing on our own, so that we know, because we know it's coming, it's going to be requested in the market.
Great, thanks, Josh. Just real quick, Josh, could you stop sharing your screen just for
Yeah,
us here? And then, Josh, also again on the biopolymers, PLGA is a biopolymer, right?
yes.
Okay, so again, that's one that we've done some work with. So if there's an individual that was asking a question about that, if you want to contact us directly, we'd be happy to share more of the details around that polymer and what we've done. There's certain polymers that we've done a lot of work with. There's some that we've only done a little bit of work with. But again, if there's somebody with an application and they're interested, we are always willing to do that development work, whether that's at the lab scale or scaling up something from the lab scale to the industrial scale. So one of the next questions is about converting the linear line to an infinity line. This is a perfect question. We get this one all the time. And from an engineering standpoint, and that's sort of my background a little bit, yes, it is fully possible. However, economically, it's probably not the most viable solution to get to an infinity line. So again, if there's someone out there that has a linear line, you're interested in possibly converting it, please get in touch with us. We can discuss more of the details around that option.
Yeah, I mean, the whole general way that the machine works for the infinity line is completely different than the linear line. Physics-wise, it's the same process, but yeah, I agree. Engineering-wise, it's completely different.
So the next question was on microelectronics and the application there. Again, a lot of the details on this are proprietary, but there are some things that you can find out about that on the web. There's people using basically an acoustically transparent membrane to prevent dust and water and other contaminants from getting inside that microelectronic device. Again, it's very, very, very interesting things, and really some of the details that are available online. I would say they give you 80% of what's really going on, and they've got some special sauce that they're saving for themselves. But again, I encourage anyone to look for those types of things out there on the web. They are there, but again, like I said, maybe only 80% of the details are revealed. Josh, you want to take the one on the Uniscan?
I can't see the question. I didn't see the
Oh,
question.
sorry, Josh. Oh, sorry. Right, forgot. So, Josh, the question is about our the Uniscan machine, the visual inspection system. Can that image processing system integrate with some sort of statistical process control machine to kind of help improve the process as it's going on in real time?
Possibly. We haven't done that. We haven't done a feedback control. It's more of a process monitoring for us now, just a quality and process monitoring that typically when you're forming these membranes, you're running at quite a low line speed. So, you could make some adjustments, but then you're not really going to see the change in the adjustment until quite a long time, especially for some of these thicker membranes. So it could be possible, and I would say that the visual system's not really relevant for super thin materials because you have to at least you have to be able to reflect. It's a reflective system, and you have to have enough, let's say, fibers there to really capture a good image of the material. Uh, I would say maybe 5 gram, 3 to 5 grams would be the limitation on that. So if you're making a thick membrane like a 10, 15 gram membrane, you're moving at less than a meter a minute. And the distance between the spinning chamber and so it's going to be a matter of waiting several minutes before you can see the change. But certainly you could. But I think it's more relevant for having something like an air permeability tester with an air filtration material where you're running at 10, 15, 20 meters per minute. You make a change, you see it instantly in that case. So it's not to say it's impossible, but
Yeah, I think just to reiterate Josh's point, the Uniscan was really developed as a bit of an R&D tool, and then an R&D tool that can help you monitor production as it goes along, just to get sort of a count of the defects that you have in your material. But again, like Josh said, there's really a limitation on the applications where you can use it. It is far from a universal solution for counting defects in nanofiber materials. So the next question is related to the belt collecting electrode and whether the seam that you see in the belt in the actual physical material, if that seam can be seen in the actual nanofiber material. And again, this is really one of those ones of it depends on the application. For things like air filtration where you're moving quickly and you're putting down a very low basis weight, no, it's very difficult to see that seam anywhere in the nanofiber layer. But on other materials, where again you have a different substrate or different basis weight, it is possible to get some read through of that seam. But again, I think we've done some things with helping to eliminate that as much as possible by
Mhm.
having sort of a finger overlap joint to make that transition as gradual as possible. But no matter what, there's always the potential to see a little bit of it.
Yeah, and,
So
and for
that,
our customers that have bought a machine on industrial scale with that belt, we've always, if there is any visual thing you can see, we always test the material on that seam or on that pattern if there is a slight pattern, just to make sure that that's not a place where you're going to see any difference in performance for the material. So Visual can sometimes be deceiving, that it may not even actually impact, or you may not see it in any testing at all, even if you see some kind of visual pattern. So I'll just make that comment.
Great, thank you, Josh. So the next question is about feeding inert gas during the electrospinning process. So no, we do not use inert gas in the actual formation of the nanofibers, at the actual site of the jets along the spinning electrode wire. However, we do use inert gas in our industrial machines to provide a sort of a inert gas, let's say, buffer above the polymer solution in the tanks, just to make sure that if there is any solvent in there, that you never create an explosive environment. Again, most of the solvents, we don't have to worry about that thing, but using the inert gas is just a nice level of additional safety when you're working with any polymer solutions that involve any sort of solvent. So again, thank you for that question. In terms of humidity control, yes, there is no question. Everyone who works with electrospinning understands very much that temperature and humidity must be maintained at a constant level to get good nanofiber production. So as Josh mentioned, we produce our own air conditioning equipment that we provide to our customers that integrates directly with our equipment. And one of the things that we do is we actually have there's a couple different sort of add-ons that we've developed over the years. One is we have what we call the tents. Those sit either before, in between, or after the nanospider units, and those basically help provide a buffer zone of humidity, of proper temperature and humidity, where if there is any mixing from the outside, because you always have to have the pass through for the substrate, so that's always going to provide some sort of an open channel. So those tents help to minimize that mixing. And then if you're working with a polymer solution that's even more sensitive, then we've helped many customers build what we call room in the room, which then is making sort of a box around the entire nanospider line. And then you condition the air inside that small nanospider line chamber, basically, to help, again, alleviate any potential sort of fugitive humidity from getting into the electrospinning process. So again, that's something we've definitely dealt with over time, and we definitely understand what can be done to mitigate those risks. So the next question is just about somewhat about the safety of nanofibers, and just from an environmental standpoint, what would environmentalists say about adding sort of more microplastics into the environment, and ours would in some way would be considered nanomaterials. But Josh, I don't know, can you comment a little bit more on the safety aspect of things?
Yeah, I mean, about the microplastics, it's hard to say. I mean, I think, almost all the plastics and nonwovens and things are generating microplastics. Of course, it depends on what you do with the materials after they're used. If they're burned, a lot of times, like, you have filters, for instance, air filters that are used, and they would, even if they're made out of the same material, it's really hard to recycle them because you have contaminants and dust in there. So the person that gets the recycled material afterwards is going to have some junk in there. Um, Environmentally, I mean, when we talk about nanomaterials, a lot of people like to classify nanofibers from, polymer nanofibers into this nanomaterials class. The big difference is that the aspect ratio of these materials, these nanomaterial or nanofibers made from electrospinning polymers, are, almost infinite. You have much longer. It's like a bowl of spaghetti, and they're also have cohesion between them when they collect. They stick together, so you don't really have that issue with having fugitive particles or nanofibers. We've done some testing in the past where we're cutting materials, slitting them, processing them, handling them, and we didn't see any significant generation of nanoparticles into the air. So in that case, it's hard to say about the microplastics. Of course, you're already smaller, so the breakdown, the degrading of the materials would be faster than higher, thicker fiber. But um, I don't envision a world where we don't have plastics. So that's the other side of it. Um, but anyway, I think, just to distinguish between, for safety purposes, to distinguish between nanoparticles like nanorods and and really particles, spherical particles, and nanofibers made from polymers made from electrospinning. It's a big difference in terms of safety. So.
Great. Thank you, Josh. So the next question was in regards to sort of the cost split for let's say a $3 per
Yeah.
linear meter material. And again, the how the cost breaks down for our material, it varies widely depending on what it is you're doing. Elmarco has a fully burdened cost model where we can help model out those things, but our sort of rough starting point is always approximately 1/3 of the cost is for depreciation, another third is for labor, and then another third is for all the other input materials, be that the polymer, the solvent, the electricity, all the facility, all of that. So that's just a like very, very rough breakdown, and that will really, the answer just varies completely, depending on what it is what it is you're actually trying to produce. So again, another question in terms of converting our machines. Someone interested in possibly adding an endless belt to an existing linear line. This one, again, engineering standpoint, yes, it is possible. However, economically, it is likely an infeasible solution because of the infrastructure that has to be there to not only support that endless belt, because it's quite a heavy piece of equipment, but then also the drive mechanism. So the motor, the gearbox, the sort of the axle, or not axle, the drive shaft to power all of that those things are very, very difficult to retrofit into a machine. Okay, so Josh, the next one is on the ability to predict things like fiber diameter and fiber properties, ahead of time, before you've actually started up the process. And I think the answer is we wish there was a way to predict it, but from everything I think we've ever experienced, the formulas can help guide you in a general direction, but you really just have to do the work and do the design of experiments to really understand, a given polymer for a given application at a given basis weight on a given substrate. There's too many variables in there that are very, very hard to map into a sort of neat formula that can just take all the inputs and spit out an answer on the other end.
I
Anything else
agree.
to add to that, Josh?
Yeah, I think it's difficult because there's so many variables, and then sometimes you would say I need to adjust by 1%, but then all of a sudden you don't have enough solution strength to form a fiber, and you're making your electrospraying or something. Yeah, and the interesting thing is, for instance, with nylon, we're spinning solutions that are 150 centipoise, and then for polyurethane, it might be 1,000. So it's like, to say if you had your model for nylon, you put in 1,000 centipoise for your viscosity, it would be like, off the map. But then for polyurethane, it makes sense. So it's just because it's there's so much interaction between all of the different variables that it's very difficult, even the humidity and temperature, throwing that in there. And that's how fast the materials dry, or how fast that they flash out of solution. So it's very difficult to do. I mean, you can probably model a specific system with a specific polymer grade and a specific solvent, and then get a really good correlation. But then as soon as you change one of those things, all bets are off. So maybe a supercomputer can do it, but maybe quantum mechanics
Next year, right, Josh? Next year.
next year. That'll be next.
Okay,
That'll
next
be our
year.
next update.
Very good. All right, so the last question we have for today is in regards to polymer recycling, and just how that plays along with electrospinning. And I certainly know that there's companies out there that offer recycled versions of some of the polymers that we use, that Elmarco uses. And while I mean all of that is fantastic, and it's all good and helpful. However, one of the problems is that even an Elmarco industrial machine on a yearly basis, still only uses, 100, maybe 200 kilograms of polymer. So the use of polymer, the actual, like the dry pellets, is quite low. So it's very hard for electrospinning to have any sort of big impact on overall recycling or overall use of recycled polymer materials. Now, again, that's not to say that any of these things don't work on our equipment. They certainly would. But again, like I said, just the overall impact is going to be pretty low.
Yeah, I would say that also using recycled polymers can, if you've got a big variation in molecular weight or something like that, it could be a big impact on the performance of the materials. You might waste more polymer trying to optimize every batch of material than you would actually save by recycling. But on that note, we do have a lot of interest now coming from the industry about making recyclable, let's say making materials that membranes you can put into, let's say, a jacket that would be polyamide based or polyester based, but polyamide based mainly, so that jacket would be considered, all polyamide, so it could be considered a recyclable material, for instance. So on that back end, we're getting a lot of interest in recycling, and then the other things about recycling the materials after spinning them. It's just a matter if you're making a filter, you're capturing things, and those things you don't want those things in your batch, your master batch after you recycle it. I don't think so. That's the other challenge with that. But
Great. Thanks, Josh. So one sort of follow-up question. In terms of the contact information for myself and for Josh and for Elmarco, all that will be provided to all the attendees. My colleagues here from the marketing department, they'll be sending that out in the next few days. And then maybe about how long for the webinar to go up on YouTube? Next week? Okay, so sometime next week, before the holidays or so, we should have the webinar up on YouTube, so you can look at it there. And again, all of those contact details will be sent out to all the participants in the webinar. So again, thank you for that question. And then the sort of part two of that question was in terms of collaboration on research, and the answer to that is definitely a wholeheartedly yes. There's many different ways to participate with Elmarco. You can just do straight up sampling where you just tell us what you want, send us some substrate, we'll coat it with nanofibers. You can form a JDA with us where we're doing some joint development on something where you have a concept but you need some help on it. We'll even do contract research and development, where again you just sort of send us off in a particular direction and then we come back and in an agreed upon amount of time and tell you the results. We're very, very flexible in terms of how we do research on nanofibers and nanofiber products for both academics and industrial customers. Again, encourage everyone to contact us if that's something that's of interest to you. And also, again, for more on the academic side, if you do have an interesting nanofiber idea, but you don't have some of the resources at your disposal, you can look up the information about the Elmarco incubator. Again, we'll make sure that gets included in the follow-up email from this webinar. And again, you can also go on to our blog and find more information on the incubator. So with that, I see that we are just about out of time. Really appreciate everyone attending. Really appreciate all the great questions. Thank you to my colleague, Josh Manasco, for his excellent presentation. Chock full of details. I'm sure everyone has more questions. Please feel free to get in touch with us. And with that, thank you so much. Enjoy the rest of your day, and we will see you next season.